Yes.
All right, so for those of you who missed last week, we were still covering enthalpy, entropy, and spontaneity. So, just as a review, enthalpy is the change in the amount of energy in a chemical system, which typically means heat. Okay, that's easiest to measure. That's what we're going to be talking about when we talk about the change in enthalpy. And in order to find the change in enthalpy of a chemical reaction, you take the change in enthalpy of the products minus the change in enthalpy of the reactants. That is because that is the amount of energy it takes to form each component within that chemical system. And so, since the products, since the reactants have already been made, that energy isn't calculated in. So that's why we have to subtract that out. So, for example, here is 2 moles of carbon monoxide plus 1 mole of O2 forms 2 moles of CO2. So what we have to do here is look at your handy dandy thermodynamic table, and we are looking for carbon monoxide, which, if we look at this, has a heat of formation, so that's the column that we're looking at, has a heat of formation of negative 110.5. We have oxygen, which has a heat of formation of 0 because that is its natural state, and carbon dioxide, which is negative 393.5. So what we do is we take that information and we plug it in. So we take our change in enthalpy of our products, which in this case would be our carbon dioxide. We have 2 moles of it, so we're going to take 2 times negative 393.5, and we're going to subtract our reactants. So we said that carbon monoxide has a heat of formation of negative 110.5 and 2 moles of that, plus 0 because oxygen does not have any heat of formation. So we calculate that out and we end up with negative 566 kilojoules. Kilojoules is our unit that we are using for heat of formation. It is just, as we discussed earlier, is a way to measure energy, any type of energy, but as I said, in this case, we're talking about heat. So that brings us to entropy. Entropy is the measure of disorder within a system or within a chemical. So what that means is the higher the number, the higher the amount of entropy, the more disorder there is. So positive numbers are going to mean greater disorder, negative numbers are going to mean less disorder. So if we think about that, a gas, so if we think about water, it's the same chemical. If we think about water in 2 different situations, one as a liquid, one as a gas, liquid water has molecules that are very close together, that are sliding past one another, but are still relatively ordered. The gas is more disordered. It has particles that are bouncing all over the place, taking up as much room as possible. And so what happens is the entropy of a gas is significantly higher than the entropy of a liquid. So that's what we're trying to look at, is how ordered is it? Is it organized? Are they moving around? Are they bouncing all over the place? If they are bouncing all over the place, if there's a lot of space in between them, they are going to be more disordered. And the way that we find that is, looks very similar. The change in entropy equals the change in entropy of the products minus the change in entropy of the reactants. So pretty simple to remember. So different equation, but we're going to go back to our handy dandy thermodynamic table and find the things that we're looking for. So our first item was hydrogen gas. Well, we're not looking at the heat of formation anymore. Now we're looking at the entropy. Okay, so we look up here, we have that S. We look at entropy, and we have H2, so it has a value of 130.7. And if we take a look at our label, it is joules per mole Kelvin. Okay, or you could just say joules per Kelvin. You can see it written slightly differently in some places. Our next item is O3, ozone. So if we come over here, ozone has 238.9 as its entropy. So it is fairly disorganized. And then the last thing that we have is water. specifically water as a gas. So 188.7. And if we take a look at this, as I just said, we have water as a gas and we have water as a liquid. The water as a gas has a significantly higher entropy, so that is saying that it is more disordered. The molecules are bouncing all over the place. There's a lot of space in between them, and they are flying past each other very, very quickly. So that's the difference between the 70 and the 188.7 here. So we take that information just as we did before. We have our product, which is the water as a gas. We have 3 moles of it, so we take our 188.7 times 3. That's our only product, so we are going to subtract all of our reactants. We have 3 moles of hydrogen, which has an entropy of 130.7. Multiply that, and then add our entropy of ozone, which is 0. And that gives us 174 joules per mole Kelvin. All right, our last item is spontaneity. The easiest way to summarize spontaneity is, does it occur on its own? Does it need to constantly have new energy put into it? And the example that I like to use on this is an avalanche. Once an avalanche starts, you do not need to keep putting energy into it in order to allow it to continue. A ball will constantly roll downhill, but it takes a lot of energy to make that ball go back uphill. It's not spontaneously going to go uphill. And surprise, surprise, our equation is change in G, which stands for Gibbs energy, named after the scientist who discovered it, equals the change in spontaneity of the products minus the change in Gibbs energy of the products minus the change in Gibbs energy of the reactants. So I'm not going to go through a sample problem on that one because it is incredibly simple. All you have to do is go back to your thermodynamic table, find your Gibbs energy, and do the same thing that we've done for the last 2 problems. However, here's our issue. The enthalpy, entropy, and spontaneity and the temperature, all 4 of these things all influence each other through the laws of thermodynamics. So here's the issue, though. We have the same reaction for all 3 different situations. But Mike, you say, why do I have to know 3 different equations that are all set up the same? The only difference is we're using different numbers. Here's the reason. They each mean something different. The enthalpy is telling us the amount of change in energy. The entropy is giving us the amount of disorder, and the spontaneity is telling us whether or not the reaction is spontaneous. So with enthalpy, the change in energy, if we have a positive number, it's an endothermic reaction. If it's a negative number, it is an exothermic reaction. With entropy, if the higher the number, so if you have a positive number, then that means you are getting more disorder. If you have a negative number, you are decreasing the amount of disorder. And the last one for spontaneity, if it is a negative number, the reaction is spontaneous. If it is a positive number, the reaction is non-spontaneous. And if it is 0, then it is at equilibrium. So it's not going to move in either direction. However, because all 4 of these items interact with one another, we get a 4th and final equation that looks like this. The change in Gibbs energy equals the change in enthalpy minus the temperature in Kelvin times the change in entropy. Okay, so we're going to work through some problems on that today, but hopefully that catches you up from last week. Oh, I'm sorry. I do have one problem that I wanted to go through with you. So here's some sample information. A reaction has a change in enthalpy of negative 76 kilojoules and a change in entropy of negative 117 joules per Kelvin. Is the reaction spontaneous at 298.15 Kelvin? So it's just a word problem. You're plugging in the information that has been provided to you. So here's our original equation. Now we plug in, we have delta G. So what's our delta H? Negative 76 kilojoules. We are going to subtract the next product. So we need our temperature in Kelvin, which is 298.15 Kelvin. And we're going to multiply that by our entropy, which is negative 117 joules per Kelvin. However, if you notice on this, I've had to change the joules per Kelvin into kilojoules per Kelvin so that my labels for these two items are the same. So after I calculate all of that, I end up with negative 41, but in order to see what my final label is going to be, I have Kelvin times kilojoules per Kelvin. So essentially I'm dividing by Kelvin, so that those two Kelvin are going to cancel out, leaving me with an answer of negative 41 kilojoules, a measurement of free energy. We're going to do some practice problems on this today, so if you have questions, please let me know.